chemical physics in the Russian Academy of Sciences. He continued to University of Bath, and then in Oxford, and then became faculty at University of South Florida, where he is since. Well, as he'll tell you, he's working on designing new kinds of materials. Please.
Thank you for introduction. It's a great pleasure to be here. It's a wonderful country. It's my first visit to Israel. I'm very impressed with what I see, especially the people that interacted. It's very warm feeling to be here. I'd like to thank Press for inviting me to participate here. I'm going to talk about the first principles of discovering new materials. But before I go into the subject of my talk, I probably would like to make some introduction of my university. The University of South Florida is a little bit misleading name. So South Florida is here around Miami. We are here in Tampa. It's by historical reason the university started at this place for Mars and then we moved into Tampa.
Please switch the lights on.
What?
There you go.
All right. So it's a zoom in on the map. So this is where the university is. This is Tampa Bay. It's a very big area. St. Petersburg is in Russia. It's here in Florida. And the university is very young. So it's a 60-year-old university, but it's one of the largest universities in the United States. It's around 50,000 students, large fraction of undergraduates, around 20% by graduate students, and we have a very energetic and very important medical school. And we are classified as within the top 40 research-intensive universities by U.S. Carnegie Foundation, and it's judged by the amount of the funding. So this is 500 million awards and grants in 2015-16 academic year. This is my group. This is our physics department. We have a very nice building that was built 10 years ago. We occupy 3 floors, 3rd, 4th, and 5th. In the building, it's called interdisciplinary sciences. We have some biology labs, we have chemistry labs, we have on the top floor, we have the Department of Biomedical Engineering. These are my students and postdocs. Some of them contributed to this work, especially Greg Steele. He graduated here as a Lawrence Limon National Laboratory postdoc. Right now, Jonathan Wilman, Kian Graham Cohen, and Joseph Gonzalez. So these are the efforts within my research group. The topic of today's talk is about discovery of new materials, but the mostly interested in genuine materials at extreme conditions, specifically shock and detonation physics, energetic materials, 2D materials, and we also developed some new atomistic simulation techniques to do the large-scale molecular dynamic simulations. So this is a brief summary of what I'm going to talk. I'm going to talk about the crystal structure prediction. It's something that it's important for you to understand that now we can do some wonderful things. We can predict something that we couldn't do this before. And the application of these methods will be mostly on this discovery of new high nitrogen content energetic materials. So these are explosives. Most of the research is funded by U.S. Department of Defense and Department of Energy. I briefly mentioned about other applications that are important for fundamental physics, hydrogen interpolation, prediction of some late materials, new late materials, and also some high temperature superconductors. So this is the motivational slide of my talk. Usually when you put some piece of material, so actually it's a mixture of materials, some precursors, and you compress, and usually the compression pressures are pretty high, around 100 GPa. So if you compress by this amount, and the volume is very small, so PV type of energy, so it's around several electron volts. So it means that you can modify chemical bonding by applying high pressure. And usually how experiments are done, this is the two pieces of diamond angles. You put some material, you apply this high pressure, then you use X-rays to do the X-ray diffraction. In addition, you can also get some Raman spectra, so this is the frequency versus intensity. And based on these two pieces of information, experimentalists try to guess the crystal structure from the complex chemistry that's going on under high pressure and high temperature.
And could you just say pressures in units of atmospheres or something like that?
So it's 100 GPa is 10 to 11 pascals, and it's 10 to 11 pascals, so 10 to 6 bars. Yes. So 10 to 6 bars, but I'm going to use GPa. So GPa is 10 to 9 pascals. It's 10,000 atmospheres. And as I mentioned, the major instrument for the identification of the crystal structure is X-ray diffraction. And we know that there were several Nobel Prizes starting from the beginning of 20th century. Lowe and son and father Braggs, and recently a couple of other people. But basically, what you do, you have the intensity peaks versus the diffraction angle. You try to identify the atomic planes, and based on this Bragg condition, you try to guess the crystal structure. So it's very, very labor intensive, especially at extreme conditions when the peaks are not very distinct. So then the question is how we can help to understand this type of experiments, but most importantly, can we predict what's going on during the experiment? So we know the initial conditions, we know what we put inside of this diamond cell, we compress, we heat. Can we predict what kind of material is going to happen? And so the usual thing, what you can imagine, so this is the statement of my problem that I'm trying to address. So given initial chemical composition and given the initial conditions, pressure and temperature, can we predict what kind of compounds we can get, what kind of reactions we can get? And in general, you need to predict not only stoichiometries, but also the phases, different phases of this material at a given pressure and temperature. But this is the example. So we shuffle some atoms and we would like to see, can we predict these compounds? So this is actually the result of our simulations that I'm going to address later. But this is the statement of the problem. And this problem was very difficult. In 1988, in Nature, there was an article specifically addressing this issue, that it's, at this stage it was unknown how we can predict the structure of the compound given its chemical composition from the knowledge of the chemical composition. And specifically it was the question of how we can understand that graphite is a little bit low in energy compared to diamond. And at this point, 1988, there were some limitations in terms of the computational power, in terms of the method that they were going to use. So there was no efficient and accurate relation of the total energy of the system, quantum mechanical method for relation of the total energy of the system. there were no efficient algorithm for searching for crystal structure. So basically what I'm going to do, I'm going to put some atoms at a given composition. I'm going to move these atoms, and based on the potential energy surface of this ensemble of atoms, I'll try to find the global minima as well as the local minima. So this is what I want to do. And there were no such algorithms for searching for the global and local minima of the potential energy. But the most importantly, there was not enough computational power. So the first item in order to do this type of things is to calculate the energy of the ensemble of the atoms. So basically, we put some atoms of known chemical elements defined by the Z, the charge of the nucleus. Based on this information, we will try to calculate the total energy of the system as a function of the coordinates of the atoms. And probably some of you, and most of you, know that there was important development in theory by physicist Walter Korn, who got the Nobel Prize in chemistry for developing density functional theory. And basically what you do, you solve the one that actually showed the problem. The most important physics here in the exchange correlation potential. There are some very powerful computational codes, so you don't need to go through this theory. It's like in experiments, it's like the piece of equipment that we as theorists and simulators use. We plug in this information and we run the simulations and we get the answer. So if we have the energy of the system as a function of coordinates of the atoms, we can move these atoms to minimize the energy, and we start exploring the potential energy surface. So this is 3 n degrees of freedom, so each atom is within this n, so n number of atoms, 3 n the number of the Cartesian coordinates of these atoms, and we minimize the energy, and we try to explore this complex potential energy. We try to find the minimum of this potential energy. So if you start thinking about the complexity of the problem, you will be amazed how difficult is this problem. So for example, I have the volume and number of atoms. I know approximately the size of this box, so it's a order of chemical bond between the atoms. So you can divide this space, 3-dimensional space, into these cubes, and you try to find and you go through different combinations, different positions of the atoms, and you try to get the number of the different combinations that you can get by moving these atoms around just randomly. So if it's one atom, it's one combination. And it's, in terms of the density function theory calculations, it's 1 second. Okay? If you have 10 atoms, it becomes 10 to 11, it takes 10 to 3 years. Okay, go 20, 10 to 17 years, and so on and so forth. So this is straightforward method of just putting atoms one by one in these cubes is intractable. We know that it's intractable. So what you can do, you can just randomly throw in the atoms and relax them, and you can get some structures. You can get one particular random configuration. You get this particular lead compound tin sulfide. Then you start with the different random configuration. You might be lucky to get this one, and so on and so forth. So this is another important development in the theory. So these are so-called crystal structure prediction methods. Mostly they are based on the evolutionary ideas of the exploring of the potential energy surface. You see how complex is this potential energy surface, and there were several important developments within the last 10 years, different methods, but they basically explore the same idea. So you have this very complex potential energy surface, and there are some simplifications that you can exploit. First of all, is you randomly ensemble the atoms. They don't want to put too close to each other. They want to form chemical bonds. We know more or less chemistry, so we know particular types of atoms form the bond lengths of a particular length. So basically, you go to local minimum once you start with the random structure. So you have plenty of random structures, but also there are so-called Bezier fractions. So if the minimum is deep enough, most of the initial configuration configurations, you go after relaxation to this point. So intrinsic dimensionality can be reduced. So how this evolutionary crystal structure search method works? So you start with the random configuration of the structures. So actually you create a generation. You have hundreds or several hundred of these random structures. Okay, so this is your first generation. So you have the population of your generation. Okay, and then basically this is a random sampling of the stoichiometry, space group, lattice parameters, atomic positions. Then you take this generation and relax using density functional theory at a given pressure at a given volume. So pressure and volume, actually pressure is fixed, volume is relaxed. So you optimize the lattice completely. You change the bond length, you change lattice parameters, you change the angles, you change the space groups, and so on and so forth. Actually, space group is not fixed because it automatically comes after the calculation. So once you relax the first generation, you classify the structures based on the energy, actually entropy, because I mentioned PV term at high pressures at 100 GP is extremely important, gives substantial contribution to the energy. So we work with the entropy, so it's energy plus PV. And we take the lowest part of the generation after we relax these, and we start applying the different variation operators. Basically, we slice the several structures that were close in energy and start mixing them together. And then we add some fraction of the random structures. And then we can continue to create the second generation of relax and do this variation operators. Do this again, until we get something that's stabilized. So I'm going to show you something how it works in practice. The important thing before I will go to the results of these methods, I need to explain how we work with the energetics. So if you have some particular random structure, initial random structure, we relax to get this particular compound with the specific space group. This just comes out of the calculation. We calculate the formation entropy. So basically it's the difference between the entropy of the compounds minus the entropies of elemental compounds at a given pressure in temperature. Okay, so we work with this formation entropies. And then we construct so-called convex hull. So what is the convex hull? So in this case, it's a binary compound. So this X and Y, they are varying during this method is powerful enough. You can change the stoichiometry when you do this evolutionary crystal structure search. So this is the composition. This is the number that specifies particular stoichiometry, and you have some structures that came out of your search. And we define so-called fitness. Fitness is the distance between this line and this particular point. So what is this line? This line is called convex hull. So convex hull means that I connect the lowest energy structure by the segments, but for example, I have another compound that is here. I don't draw this line here because I know that if this compound is above this line, it will decompose into A and AB. So this is what is called convex hull, right? So then we determine this convex hull for a given pressure, and this is how this convex hull evolves for each generation. So before this convex hull, I have to relax the structures within the generation. Okay, and I said that we work with the entropy, and the important thing that these are points that correspond particular stoichiometry 1,1, this 1,4, and these are the thermodynamically stable compounds, right? So it means that if you have compound here, okay, we call it metastable. We specify the metastability by the distance from the convex hull, how energetically it's above the convex hull. So although this point is not thermodynamically stable, it might be metastable. Metastable means that it's locked into local potential energy minimum. Okay? And we check whether it's potential energy minimum by calculating Phonon spectrum. Okay? So these are just the illustration of the variation operators. So we take the two parent structures, we slice them, mix together, show heredity. So we have the lattice mutation, soft mode mutation, permutation. This is the technology, so I don't want to go into the technology. But this is how this complex all works. So this first generation, we have some points here. Then we do generation 5. Then we see that new compounds start appearing, generation 11, generation 15. And we run this search for many generations until we see that complex all doesn't change for the last, for example, 10 generations. So it means that we completed our search. Theoretically, it found impossible. We didn't find all the compounds, but because of the complexity, we just stopped because we cannot run the calculations correct. And as I said, that this is a particular example of the tin sulfur compounds. We see some different stoichiometries, and we look at the structures, and then what we do, we characterize the structures by calculating different properties: electronic, vibrational, optical, and so on and so forth. So this is how it works in the case of tin and sulfur. So we look at the lowest one, this 1 stoichiometry, we get this one. This is known, by the way, it's non-compound. The key thing that we don't use experimental information, this is how we test that our calculations work. We predict non-compounds. It's an important test, okay? Especially at ambient conditions. Then there is 1, 2 compound, but then we predicted a new compound that I'm going to talk later on. So then once we predict compounds, we want to make sure that this compound is stable. As a rule, all the thermodynamically stable compounds, we didn't see any cases when we found, we predicted from a thermodynamically stable compound, it's unstable. If it's unstable, you need to search it again, explore the same stoichiometry, find the different polymers of the given material. Okay? But you look at the phonon spectra, so this is the vibrational frequencies versus the Q vector, right? And you look at the modes that have imaginary modes, so they plotted as with the negative frequency. If you have the structure with imaginary modes, it means that it's not the local minima, it wants to slice down to somewhere else, right? And so in this particular case, at 0 GPa, one particular compound, this new compound that we discovered, is unstable at ambient conditions, but when you apply the pressure around 30 and 100 GPa, we see that this imaginary phonon mode is gone. Right? So I explain you how this method works. I want to show you our recent discovery of new high nitrogen contact energetic materials. So the motivation of this work is the following. So if you look at the nitrogen-nitrogen bonds, we know that the stable compound in ambient conditions is NaN₂ molecule. So nitrogen-nitrogen system is very unique in the sense that the difference between single, double, and triple bond is quite remarkable. If you compare this with the carbon, you see that when you go from the single to double bond, this energy of the bond triples. If you go from the single to triple bonded, you see that it's 6 times the difference between N2 and single bonded nitrogen. The question is, how we can get the single bonded nitrogen? If you get the single bonded nitrogen, that we know that at ambient conditions is not the ground state structure. If you have this metastable structure, single bonded metastable nitrogen-nitrogen structure, and we provide some stimulus, it must decompose in N2 molecules. And this huge difference in terms of the chemical bonding must be released, right? So this is the difficulty with the nitrogen-nitrogen because it's difficult to get single bonded nitrogen. Okay, so we know that the polymers of nitrogen are unstable, stable monomers. In case of the carbon is opposite things. So carbon wants to form the polymers, long chains of the single bonded carbon-carbon bonds. It turned out that such structure of single bonded nitrogen theoretically was predicted to exist. And if this structure can be synthesized and you can get this material compound, and start working with these, it will have the 10 times power of the currently non-energetic materials because of this difference between single and triple bond. So this single bonded form of nitrogen was predicted theoretically by 1992. It's called cubic Gauss structure, and it was predicted that there is a stable structure, 50 GPE. Experimentally tried many times, but in 2004, Hermetz and others, they synthesized this at 15 GPE and 2000 Kelvin. But what is important is that the single bonded form of nitrogen wasn't stabilized at ambient conditions. Once the pressures were dropped, this cubic Gauss nitrogen decomposes into NaN₂ molecules. So then there was a substantial effort at the beginning of 2000. This effort was funded by DARPA, so it's Defense Advanced Project Research Agency in the United States. And people started looking at not at the extended solids, but started looking at chemists started looking at the not N2, but N5, N6, and so on and so forth, some molecular clusters of the nitrogen. There is one that exists, it's called azide group, so it's N3 minus. There were some experimental discoveries of these clusters, but most of them were unstable, they decompose at the ambient conditions. So the idea was, when we started this project, let's look at some alternatives. So let's start adding something to pure nitrogen. Can we stabilize the single bonded or double bonded, at least, nitrogen in our work? And this project was done in cooperation with both theory and experiment. Theory was provided by my group. I worked with the people at Lawrence Livermore National Lab. They do the experiments, but we pursued a completely different approach. We wanted to predict the compounds first, provide some justification, provide the information about precursors, provide the information about the stability of these compounds, provide this information to experimental people, and guide them towards experimental synthesis. And how we do the validation, we calculate theoretical excited environment spectra and compare the experiment. This is what they measure, and when we find a good agreement, means that we are spot on. So I said that we use this variational crystal structure, evolutionary crystal structure search with variable composition, and we calculate, predict the full convex force and phase diagrams of the compounds in partial stoichiometry, calculate the dynamic stability, characterize using calculating the Brown and excited spectra, compare the experiment. This is the role of our theoretical effort. So probably I skip this, and I want to illustrate what we found. So we started with the sodium and nitrogen compound. Why did we started this? Because of the previous experimental effort, but before explaining this previous experimental effort, I want to show how this evolutionary crystal structure works. So we started at one of the first generations, we found this compound. So this is the formation entity. Then this compound evolves into lower energy structure, and then at generation 7, we got the new compound. And this compound has N5 rings. So these are called pentothales. All right? And what was the motivation why we started with the sodium and nitrogen, this particular binary compound? Because there was some experiment by Hermetz and others, they wanted to find a single form of nitrogen, but they tried different things. They tried pure nitrogen compression, which worked extremely large pressures. They tried to use the sodium azide, so nitrogen N3. This sodium azide contains N3 minus this azide group that contains double bonded forms of nitrogen. And they thought that if they heat this, compress this, they might see the single bonded form of nitrogen. So upon the compression and heating of this compound, at around 50 GPa, they see appearance of two pixels around the spectrum. There was no excited study. This spectrum wasn't explained. So they put some hypothesis what might be, but there was no explanation. So when we started research, we completed this in systematic fashion. So we did researches at different pressures, almost at ambient conditions, 10 GPa, 20 GPa,